1, in onda. Saluta.
Ciao.
Ah, ok, ci siamo.
Ciao a tutti.
Siamo in onda. Eccoci qua. Faccio avanti e indietro perché alla fine il personale è ridotto d'estate. Ciao a tutti, buonasera. Buonasera a chi sta qui, a chi ci segue da casa. Un applauso anche a voi perché siamo al 21 di giugno, fa un caldo boia e già si suda. E si suda perché siamo a Roma, questo è RomaJS, il meetup della capitale che sfrutta il JavaScript come lingua franca per chiacchierare di un po' tutto ciò che riguarda lo sviluppo informatico, pattern, librerie, framework, metodologie, eccetera, eccetera. La cosa fondamentale poi, oltre al meetup che organizziamo una volta al mese, il terzo mercoledì, con un bellissimo talk, bellissime domande, bellissime chiacchiere, e poi la parte anche di community dopo, quindi canonica è la cena con la birra e il networking che segue. Quindi ci dispiace per chi è da remoto, è un'occasione in più la prossima volta per venire. E il meetup è tutti i mesi, il terzo mercoledì, quindi potete già mettere in calendario il prossimo, non agosto, poi riprenderemo a settembre. E fa veramente caldissimo, quindi le presentazioni andrei molto, molto rapide. Faremo dopo il conteggio per chi viene a cena. E, cosa importante, gli speaker di RomaJS sono maggiormente persone che vengono dalla community, non ci sono aziende dietro, non siamo una community che si auto sponsorizza e si autoalimenta. Quindi se avete idee per talk o volete sentir parlare di qualcosa in particolare, contattateci, proponetevi, anche se è la vostra prima esperienza, cerchiamo di dare un po' una mano a chi è alle prime armi con le presentazioni e che vuole fare questa esperienza qua. Per il resto del mese, quando non ci vediamo, il terzo mercoledì del mese, questa cosa di ripeterla è sempre molto marketing, ci troviamo sul canale Slack, romajs.org, ci sono tutti i link social, entrate sul canale Slack, poco spam, abbastanza contenuti utili, e poi si entra in contatto con il resto della community per tutto il mese, tutto l'anno. Detto ciò, molto semplicemente, molto diretti, questa sera parliamo di un argomento molto avanzato per cui lascio Luís poi parlare, però diciamo di motori di ricerca.
Più semplice di quando sembra.
Più semplice di quando ricerca, questo lo stabiliremo alla fine, però per il momento è un argomento molto figo, con motori di ricerca e in JavaScript. E lascio la parola a Luís, il nostro speaker.
Grazie.
Vai Luís.
Grazie, buonasera. Questo lo farò in inglese come annunziato.
Come già annunciato.
Okay, I'll switch to English. First of all, thanks to the community for hosting me here, and thanks to Immobilier for this space. So Bloom filters is something that's been interesting me for the last couple of years, and I've started thinking about using Bloom filters to search even before, I was working for Neustar as a staff engineer. So this is me. Because I'm very interested in the gem stack. Building a static site, maybe enhancing it with a few external APIs, some JavaScript, but mainly the static website part is the one that interests me the most. And because most of my personal sites are static, I wanted to enhance them with a little search engine. So if you have a blog hosted on WordPress, the search engine comes for free. But if you don't, then you have to rely on an API like some external service like Algolia that provides a search for whatever data you have. But that didn't interest me because I wanted everything to be local on my site. So there are some advantages to client-side search. Everything is self-contained. If your site supports service workers to enable, for example, offline mode, then your search will also work offline. Privacy is pretty much built in unless you put in some code to communicate the queries to some service. Obviously, it requires JavaScript because you can't run logic on the browser otherwise. And there is a little caveat, which is the index size of your search engine needs to be really, really small, because if you have a reasonably large site, and I'll show you some examples, you can have a search index that can get up to 5, 6, 7, 8 megabytes that have to be downloaded by whoever's visiting the site. That's not very nice, especially if you're using like mobile connection, or you live in a place where network access costs a lot or is really slow. So that was a consideration. It's one of the reasons why I started looking into Bloom filters. My use case is, like I said, my static sites. So at most 100 or so small documents, either articles or blog posts or whatever you have. It might scale to thousands. It might scale to tens of thousands. I don't know. I haven't tried it. That's something to be checked. So when I was thinking about integrating search into my sites, there's a few options already that do this. So I started with Lunr and Elasticlunr, which are based on these data structures called inverted indices. If you're familiar with Elasticsearch, for example, or anything based on Lucene, which is the underlying engine of Elasticsearch, you'll have worked with this. Inverted indices are pretty powerful in terms of the types of queries that they support. So you can do fuzzy matching, for example, but they tend to be really big. There's a similar, maybe a little more compact option called context indices that are provided by a library called FlexSearch, which unfortunately I couldn't get to work. It works fine, but then I can't serialize the index to put on the website to download. So that was the end of that. There's also something called MiniSearch, which implements a radix tree. It's sort of like an inverted index, but it's even more compact. It's more limited, but even more compact. And then I thought, no, I'm not going to do any of these anymore because the indices are too big. I didn't know radix tree at the time, which was pretty good. If I'd known about radix tree, I probably wouldn't have made the BloomSearch engine. But the others were too big for my liking. So I was dealing with indices of 8 megabytes, for example, which was not good. So BloomSearch, highly experimental. It was like a pet project that I've had for the last couple of years. So what's a Bloom filter? The Bloom filter is a data structure that it's a probabilistic data structure. And it's designed to answer a single question. Is this thing in this collection? Each Bloom filter represents a collection of entities. And you can ask about anything that you can serialize or you can put into the filter. And I'll explain in a bit how it gets added there. Bloom filters can only answer this question in 2 ways. Probably yes. So it may or may not be in this collection, or it definitely is not in this collection. Good example of Bloom filters in action. So if you use virtually, I guess, any browser nowadays, so you'll probably know that if you try to visit like a dodgy site, the browser will warn you. This site might not be secure. Are you sure you want to continue? It might host malware, etc. So this works thanks to a Bloom filter. Google Chrome, for example, it doesn't go and check with Google every time you visit the site. It still sends, whatever site you visit to Google, but because asking Google to check on a site before you visit would introduce a delay in the network connection, what they actually do is they keep a Bloom filter locally in the browser, and they check this Bloom filter. So if the site is definitely not in the collection, so if the site is definitely safe-ish, then you're allowed through. And the worst that can happen is you get a false positive. It says, it probably is, but we're not sure. Then it checks with Google, and Google tells you for sure, now, is this dodgy or not? And this is very simple, because a Bloom filter is an array of bits. That's it. And it's assisted by a number of independent hash functions. And I'll explain in a bit how these hash functions come into play. And it's because it's an array of bits, it's really, really, really compact. That's why I was interested in the space savings potential of Bloom filters to do this. How does it work? Okay, let me switch to a little demo. Hopefully people at home will be able to see it. So I have a very small Bloom filter here. It's empty, 10 slots, 10 bits. And I've configured it to have 2 hash functions, just to give you an example of how it might work. So let me add a couple of words to the filter. I can add dog, okay? So dog goes into these hash functions, both hash functions. And each one of these hash functions will return a number. That number is the index, it's the position of the array that you're going to flip to 1. So I put in dog, 2 numbers came out, 5 and 9, and this becomes true on the filter. So if I add cat, again, I get, in this case, I only have 5 and 7. 5 and 7. Sometimes it collides, right? You've seen it here, it collides with 1 bit. But it doesn't really matter because the number of hashes provide this sort of resilience. So if I want to search, I do the same process. I run the word through both hash functions, and I check the positions. If the positions are true, both of them, then I can say probably there. But if I put in, I don't know, horse, maybe? Because one of them is missing, right? Let me clear this. Because one of them is missing, then it says, okay, definitely there is no horse in this filter. Now, I don't know if I'll be able to find one that collides, but no. That's unfortunately cow, maybe? No. Anyway, if the positions are filled by any other word, I could even put in a lot of more animals in the collection. And I do this. Okay. Snail. Fox. Okay, probably found. So there is no mouse in the filter, but because the positions are already populated, it's giving you a false positive. How do you eliminate this? You increase the size of the index. You make it bigger, so the spread is bigger, and you potentially could increase also the number of hash functions that you use so that you have more points of contact to check the filter. Okay, going back to the presentation. So this array that you've seen in the search engine that I'm showing you is the signature of the document. So one of these documents gets translated into a filter that contains all the words in that document. So I mentioned the probability of these false positives. How do we improve the error rate? Fortunately, this has been studied academically quite a lot. So there is a formula to find out what the optimal size of a Bloom filter is. Sorry. So M is the size of the filter that you want. N is the number of elements in the collection. In this case, it's the number of words in the document, unique words in the document. And epsilon is your desired error rate. So it can be 0.05, 0.00005, 0.0001, whatever you want. It can be as small as you want. It can never be 0, though. How many hash functions? Again, there's a formula for this. You take the M that you calculated from the previous formula. You use, again, the number of elements or the number of words in the document, multiply it by the natural logarithm of 2, and you get the number of hash functions. So suppose you get k as 10. Like, how are you going to find 10 different independent hash functions? And the good news is you only need 2. And there's a formula for that as well. So you only need two, H1 and H2. Those are the hash functions, unique hash functions that you need. Can be the same hashing algorithm with different seeds. That works as well. And basically, you can create any independent hash function you want from these. The hash function doesn't need to be a cryptographic hash function. That's overkill. But it needs to be a decent enough hash function because you want this to be as uniform as possible, the distribution of the numbers that you get. Otherwise, you'll get a lot of collisions in the Bloom filter. So, okay, improving relevance. So now we have this document translated into a Bloom filter. The problem is that it's a binary Bloom filter. So you only know if a word is there or not. If you're comparing the results of checking, you have n documents, so you have n Bloom filters. You can check them all, but you'll only know this word is here or not. So there is a variant of the Bloom filter called a counting Bloom filter. And the difference, again, this is very simple. Instead of a binary array, you have an array of numbers. I'll switch to a little demo. So it works pretty much almost the same. And again, you can add dog, you can add cat, you can add horse, and if you can add cat again. So if the word appears twice in your document, it increases the count. So searching for cat, we'll say probably found too. Probably, again, it's best effort because if all of the Bloom filters are already filled with numbers, it's going to give you a wrong value. Contrasting with the normal Bloom filter, this has the advantage that you can remove stuff from it. You know where to find because you know you're not removing a bit that has been set by another element. So having a counting Bloom filter allows me to check all the Bloom filters for the word that you're searching, and this will give you the documents, the relative or respective documents for each of these Bloom filters that you've searched. And then you can use these values, these numbers that you get from it, to rank the results. So if a word appears 3 times in a document and only once in another, you know that the one with the 3 comes first. This is a very naive way to rank the stuff, but it works. This is a simple search engine, so don't expect Elasticsearch with this. So like I said, one document is one counting Bloom filter. Another optimization that was relatively trivial to implement with this is the ability to require or exclude a term from your search. So if you have a require, so you put in plus and a word, you can say, I only want to see documents where this word appears, so you exclude everything else. You can put in minus and a word, and if that word occurs in a particular document, then you exclude it from the search results. Again, trivial because you are still searching for words, but this helps if you're refining a search in these in my sites. So I mentioned that ranking the counting Bloom filter results was a bit naive. So there's better ways to do it, and one of them is an algorithm called, or a family of algorithms called TF-IDF. And this is about calculating the relative term frequency of a document in the context of all of the documents that you're searching. What this means is that a word that is more unique, more statistically significant, a word that appears only in a few documents but not in the others, is more important for ranking. So you deprioritize words that appear everywhere, and you prioritize words that only appear, the words you search, obviously, that only appear in certain documents. And if these words are proportionally take more space in the document, the more important they are. So a small document with a lot of rare words gets pushed to the top. A larger document with a lot of very common words that basically exist everywhere, it gets pulled to the bottom. Okay. Another thing is field boosting. So because you're potentially you're indexing a document, not just a string, with this search engine, you're able to boost the fields, but you're only able to boost them at index time. Because once you have only the Bloom filter, and again, it's either an array of numbers or an array of bits, you have zero or almost zero information about the original document. So you can't really know if the word appeared in the title field or the author field or whatever, or a tag or a category. You don't know that. But when you're indexing it, you do know where the words are found. So the trick here is to inject it multiple times if you want to boost the field. So if, for example, you want to boost the title field, and you take the word from the title, and depending on the boost factor, you add it 10 times, 20 times, 30 times to the filter, and that artificially increases the number in the counting Bloom filter. So when you search for it, you get a bigger number back. Given the use case that I have, static sites and all that, that's fine. I mean, if you want to change how the boost algorithm is set up, you reindex everything again when you redeploy or whatever. Something else that I've added more out of curiosity to see if it could be done. I don't have it enabled because it makes the indices much bigger. Is to be able to search for a particular phrase. So instead of looking just for a word, I group them, and this is configurable in groups of 2 or 3 words in a sequence. And when you search for that particular phrase between quotes, it's able to give you some results back. But like I said, this increases the size of the index by 2, 3, 4 times. Now, performance. Performance is definitely a consideration, especially when indexing. Indexing is really slow because you have to hash every word of every document in order to put it into a filter and get a number back. Pretty easy to solve. If you memorize the hash functions, if you're not familiar with the concept of memoizing, it's the ability to take a function, and the function must be deterministic. So for each input, you must always get the same output. And you apply like a caching layer on this function so that when you call it the next time with the same value, it automatically gives you the stored value instead of recalculating everything again. So this improves indexing performance by 200% for a lot of documents. And the last thing is improving the index size. And this didn't exist until last week, because until last week, I was using counting Bloom filters to store the index of, or the signatures of the documents. And it wasn't bad, but I wasn't happy about it. So what I thought was, let's go back to classic Bloom filters. Let's go back to the binary ones, the arrays of bits. How can I store information about word counts in arrays of bits? I group them by frequency, the words by frequency. So if a word appears once, it goes on the first collection, in the first Bloom filter. So each document is now represented by n Bloom filters. And if a word appears twice, it goes on the second collection, I add it there, and so on and so forth. This obviously is not very efficient, because if you have a very big document where you have a long tail, especially if you're indexing, say, a book, you have a long tail of words that appear a lot, but they have really small indices. So towards the end, you have increasingly tiny indices, and then you have to serialize all of it, and it becomes bigger. But thinking about also how TF-IDF works, where the rarer words are more important, and it really doesn't matter for the more common words. If a word appears 60 times in a document and 62 times in another document, does it really matter if one comes before the other? So I put them into buckets. And instead of having n buckets of binary filters, I have like 7, 8. It's configurable. So if it doesn't work for you, the default, you can change it. So for the rarer words, you group them in the initial buckets. And for the more frequent words, they go on the last one. So anything that appears more than 64 times in a document, this is an example, it all goes in the last bucket. Another way to, it both helps relevance this and it cleans up the index, is the concept of stop words. Stop words are words that you do not want to index. And these are the common as dirt words, the articles, the, a, an, words that are not very, like some very, words that are so common that nobody realistically searches for them. And because they might appear in all the documents, it's really not useful to have them in the index. So this reduces the index also by a bit and improves the relevance. Another thing is the concept of stemming. Stemming is a way to, it helped me both reduce the size of the index, make it bigger. It's a way to both reduce the size of the index and allow a kind of fake fuzzy matching in the search engine, because Bloom filters, they only match because they go through this, the words go through this hash function, so they have to get a very specific value to check on the index. And because of this, you can't do prefix search. You can't do partial matching of the word. It has to be the exact word that you've indexed. It has to be the one that you search. Stemming helps you concentrate the words that are similar into the same token. So stemming is language specific. So there is a stemmer for English, there is a stemmer for Italian, there is a stemmer for Portuguese. And each one, what they do is they get you the root of the word. So you can write test, it gives you test. If you write tests, it gives you test. If you write tested, it gives you test. And so on. So you compact a lot of related words into the same token. And again, when you search, you run it through the stemmer, and you're searching for the stem, not for the original word. And finally, this is something that you could apply to any index that you have. Lunr, Elasticlunr, I started using it then, is an alternative to JSON called Messageback, which is binary, and it really compresses the payload of the index. So if you have like, an 8 megabyte file, it becomes a 3 megabyte file, which is much better. How does this compare then? Okay, Lunr and Elasticlunr, they're very similar. They're, like I said, they're both based on inverted indices. Indexing depends on the number of documents that you have, the number of words, and the size of these documents. Searching is pretty fast, and you get, like I mentioned, I mean, not Elasticsearch because this is a local search engine, but you get some pretty powerful fuzzy matching, prefix, suffix. Even if you write a word and you're off by 1 character or 2, or you miss something, you have a typo, it still is able to find something in there. It is pretty powerful, but it is pretty big. So on one of my sites, like I mentioned, the index was 8 megabytes, which was not something that I was happy with. Elasticlunr is an improvement on Lunr. It also improves the size of the index a bit, but still not enough. MiniSearch is the one I discovered more or less recently. It has a very small footprint. Again, indexing and searching are reasonably fast. Searching is fast, but it's more limited than Elasticsearch. Elasticsearch, not Elasticsearch. Lunr. And finally, BloomSearch, based on Bloom filters. It has the smallest footprint of the libraries that I've tried. Indexing is really, really slow, though, because it depends on the number of hash functions that you have. You have to run, again, you have to run every word through all the hash functions that you have. If you have a big document, it takes a while. And obviously, the number or size of the documents. Fuzzy matching is very limited. Like I explained, it's basically just using the stemmer to find the words. And there is a false positive rate, which is a pain. It can be lowered, but again, can never be 0. Time to index. Elasticlunr, it's the fastest of them all. And BloomSearch, I mean, it's not too bad. It takes 11 seconds to index. This is a sample or reference collection of documents that I took from Project Gutenberg. So it's 20 books, and I've compared them all with the same data set. BloomSearch has a little asterisk in there. It's just to say that the error rate is 0.05%. If you decrease the error rate, you get a bigger Bloom filter and a slower Bloom filter. If you increase the error rate, you get a much smaller one, but also one that gives you a lot of false information. Where BloomSearch shines is the index size, which is significantly smaller than even the biggest or the second best, which is MiniSearch. So compared to Elasticlunr, it takes 10% of the space for the same indexed information. Let me show you the collection that I was mentioning then. Oh, I'm not sharing. Okay. Okay, so little comparison. So like I said, I took 20 books from Project Gutenberg, and I ran them all through all the search engines, local search engines that I mentioned. So if you're looking for a book about a whale, you can see there are differences because each one of these search engines ranks the documents differently, the search results differently, but you're still able to get some useful information. I mean, BloomSearch is not as perfect, but it's not too far off. And for my use case, it's good enough. So if you're looking for a book about a whale, you get Moby Dick. If you're looking for a book about a vampire, you get Dracula. About a monster, you probably get Frankenstein. Yeah. So a book about, I don't know, Martians, you get War of the Worlds. Or something set in Dublin, you get Ulysses. So it's comparable in performance to more sophisticated search engines. Obviously, you don't get the search options that you get from Elasticlunr or Lunr, but that was not the goal. The goal was to have a search engine that was reasonably small. You can get it from this package, npm install this. There is no UI. This is just the raw, engine. You dump words into the documents into the index, and you query it, and that's it. If you want to build, I can share the demo that I have. You can check the source code. See, it's an example implementation of a UI for this search. But the package itself is UI-less. And that is all. Thank you. Have any comments? Any complaints?
Ok. Luís capisce l'italiano, quindi se volete fare in italiano suppongo possa andare bene.
Sì.
Tanto che ringrazio Luís e si becca la spilletta che non dicevamo prima per lo speaker, bella. Quindi è anche un incentivo in più a venire come speaker per il RomaJS.
E lo colleziono.
La
collezione questa.
La collezione di quadri. Quella l'anno prossimo magari è diversa, quindi ce n'avrai un'altra collezionaria, è il trucco con cui poi riusciamo a portare altri speaker.
Come vuoi? Capisco italiano.
Ok, allora in italiano magari c'è. Sono due parametri da configurare inizialmente per la creazione, diciamo, indicizzazione, ma che sono il numero di funzioni hash e la non mi ricordo
la taglia dell'array, sì.
È un parametro, diciamo, scelto all'inizio o è
sì.
dinamico? Okay.
Non è dinamico.
Cresce, diciamo,
no, non cresce. Quindi in questo caso tu sai in anticipo quanto grande è il documento, quindi sai quanto grande sarà il Bloom filter e quante funzioni di hash avrai bisogno. Però non cresce, non è dinamico.
Quindi diciamo, scegliendo un parametro sempre molto basso, diventa inutile perché
sì.
poi ho proprio sì. C'è un modo per capire quale è un parametro magari ottimale?
Sì, c'è questi due... Sì. Questa parte che hai bloccato perché... Questa è la taglia ottimale del Bloom filter. Epsilon è il tasso di errore? Si dice no, error rate. Vabbè. E questo è il numero di hash functions.
In caso in cui
è morto
no,
scusami, facciamo così. Aspetta. Dobbiamo fare così.
Dicevo, in caso in cui nasce il mio bacino di documenti, sono costretto, diciamo, a ricalcolare la size corretta e rindicizzare tutto. Giusto?
No, se aggiungi un documento... Scusa, se aggiungi un documento va benissimo, ma l'indice di tutti i documenti rimane uguale. Se il documento invece cresce o subisce alterazioni, qualcosa nel documento, allora deve reindessare tutto.
Guardando il tuo esempio,
sì.
10 libri,
sì.
Sai che quei 10 libri avranno 7 milioni di parole,
sì.
Quindi ti calcoli 2 valori.
Giusto, sì.
Se il mio cliente mi dice devi indicizzare anche questi altri 10 libri.
Sì, ogni libro ha un filtro diverso, un nuovo filtro, quindi aggiungi un filtro alla collection. Non cambiano i filtri che sono già indessati. Se il documento è alterato, allora sì, devi reindexare quel documento. Sì.
Aggiungo una cosa, che tra questi qui, è abbastanza recente come libreria, c'è Orama, che adesso è un altro tool, un'altra libreria di Michele Riva, diciamo, full text search, client side, non so con che approccio, quindi poi magari per il prossimo talk c'hai un tool in più da mettere sulle comparison su come l'ha fatto, però te lo lascio qualcosa. E non so se ci sono altre domande. Lui.
Ciao, innanzitutto grazie per il talk, super interessante. Curiosità, se dimensioni il numero di documenti che ti aspetti troppo piccolo, poi come diceva Enrico, potresti avere troppi clash se riempi la collezione.
Il filtro contiene le parole di un solo documento.
Ok.
Ogni documento può avere anche filtri di parole diverse.
Ah, ok.
Quindi, un documento piccolo ha un filtro più piccolo, per un altro si aggiunge un altro documento più grande, però un filtro più grande.
Ah, ok.
Un documento, un filtro. Ho un documento che poi ho cambiato.
Questo è il microfono. C'è uno solo.
Ah, scusa. Ok, quindi non devi stimare in anticipo. No, ok.
Quindi ricapitolando, poi ti ripasso il microfono, il giro è: prendo per ogni documento, calcolo qual è il numero la dimensione del mio filter che mi serve per quella tipologia di documento che voglio indicizzare, indicizzo e mi genera questa cosa. E così per ogni documento. Quando vado a fare la ricerca, itero su questi documenti indicizzati e uso stessa funzione su quella parola per vedere all'interno di quel filter se trovo l'occorrenza oppure, cioè se è possibile che ci sia quella parola oppure completamente no. Ok? Perché tanto non si sentono, quindi ok. A posto. No. Vai, adesso però faccio la valletta. Dai.
Quindi n è word count. Ok. E la distribuzione delle parole non incide.
Ti volevi, vai, se vuoi argomentare.
La distribuzione delle parole può essere l'ideale, dipende molto dalla funzione di hashing che scegli, perché poi queste parole vengono distribuite dalla funzione di hashing, non...
Certo, perché sì, le regole mi sembrano semplici.
Scusa, certo, perché se io prendo un libro, so che dentro quel libro ci sono 5.000 parole, calcolo che tolte le stop word, quindi diventano 4.000, però ci stanno i duplicati, quindi c'è un modo per calcolare o vai così a occhio, cioè da questi 4.000, in base alla lingua italiano e inglese, so che ci possono stare tot occorrenze, quindi calcolo n in base, sottraendo dei possibili numeri di occorrenza, sempre a livello statistico, immagino.
In questo caso n è il numero di parole uniche che occorrono senza duplicati. Sì.
Prendi il documento, calcoli tutte le parole.
Perché poi quando aggiungi
così mi sente molto sensibile.
Quando aggiungi la parola al filter, occupa la stessa posizione, quindi se aggiungi 2, 3, 4 volte non cambia. Devi sapere quante di quella parola esiste nel libro, nel documento, per poi in questa distribuzione sapere dove la aggiungerai. Passa questo.
Scusa, sono molto curioso. Negli esempi però abbiamo trattato sempre la singola parola. Effettua anche la tokenizzazione su più parole in fase di ricerca con lo stesso calcolo probabilistico.
Argomento, se facendo il giro che abbiamo detto prima, cerco la parola, ripassa sulla funzione di hash e la cerco nel filter. Se ho più parole, cosa conviene fare?
Se hai più parole, c'è questa opzione di indessare n-gram, di gram. I'll switch to English. There's the ability to index digrams, trigrams, quadrigrams, whatever you have. So you configure the filter when you're indexing the document, and what the indexer does is take groups of 2 words and indexes them as if they were a single word. It doesn't matter, it's a string, right? So if there's a space in there. You can, in this case, the stop words are not considered because they could be part of a phrase that you want to search. But you could potentially, all of these functions are pluggable. You can, and the stop word function is a function. So you could say, okay, there's things that I want to filter out, but that's up to you. By default, it doesn't do that. It just indexes whatever you have in the document for anagrams.
Io ho soltanto un dubbio su quando al client arrivano questi index, cioè nell'architettura completa del search, cioè io non conosco bene tutti i passaggi, cioè quando è che io client ricevo tutti questi index? Quando il server ha builda e poi io gli chiedo la pagina e mi arriva la pagina più tutti i Bloom filters. Ok. Sì, è la risposta.
Questo è come vuoi, perché l'index è un file sul server, è un file statico. Lo puoi caricare quando arriva al sito oppure quando clicchi sulle opzioni di ricerca o inizi a scrivere, ma questo lo decidi tu quando scaricarlo.
Aggiungo, come dice all'inizio, è un discorso soprattutto sui siti statici, dove non hai bisogno del server che ti elabora, generi questi indici, poi lo passi. Quando hai il documento. Poi. Domande? Altre cose? No? Capito. Una cosa... un altro applauso a Luís, che ci aveva promesso che sarebbe stato un argomento semplice. E effettivamente comunque è stato semplice, comunque ha mantenuto la promessa, quindi devo dire, cioè, abbiamo capito quasi tutti, le domande erano abbastanza mirate, quindi mi sembra che comunque la promessa è stata mantenuta. Grazie Luís. Una cosa che mi sono dimenticato all'inizio, perché sono un pessimo host, è stato anche ringraziare Immobiliare Labs, Immobiliare Labs, che è quello che ci ospita, però dentro immobiliare.it siamo nella sede di Immobiliare, che anche questo mese ci ha ospitato e ci dà la possibilità di essere fisicamente qui, e che ha preparato anche un rinfresco, un piccolo aperitivo, dove adesso andiamo, chi è in presenza, mi dispiace per chi è a casa, però chi è in presenza si andrà a godere. Quindi, a questo punto, sono le 8, precisi, e ringrazio di nuovo Luís, ringrazio voi per essere qui, ringrazio chi ci guarda da casa, l'appuntamento è al prossimo terzo mercoledì del mese, e con il prossimo meetup. Buona serata!